We were planning on going through page 7 yesterday. We actually started moving a little bit on into page 8. And when we get to this whole area of converting between unit systems, I'm going to show you that there's some things that we do in this conversion that's pretty intuitive. I mean, it makes sense to us. And my concern is that we understand how we're doing what we're doing, even when it seems obvious, even when it makes perfect sense. For example, let me say that I were to ask you to convert 2 feet, and I want to know how many inches. How many inches are in 2 feet? 24. Is there anybody here that wants to debate or argue whether there are 24 inches in 2 feet? I didn't think so. How did you come up with that answer?
12 times 2.
Okay, so in your mind you said
12 inches in the foot.
2 times 12 equals 24, right? Now, if I were to show you that what you've actually done is this very simple, very straightforward, very obvious process is the same way that you're going to convert much more complicated things later on in the course. It's the same process. Now, if you just happen to know that 2 feet is 24 inches and you say 24 inches, I get the concept, we're good, let's move on. You may not. It's kind of the difference between people who learn a language and they learn it from a whole language versus your whole language versus a phonics perspective. If you understand whole language, that means that when you see a word like over here, you've memorized what the word periodic looks like. And whenever you see these letters in combination, you say periodic, but yet you don't know how to sound out the word. Every time you come to a new word, you're lost. It's not a word, it looks just like a piece of art. I'm trying to describe my feelings about the art. No, sound it out. What does the word say? What does it mean? But see the difference? You may have said 2 feet is 24 inches, almost like an immediate gut response. You didn't even have to think about it. But in actuality, there was a process that you went through to go from 2 feet to 24 inches. Let's think a moment what that process was. And that's why I said, how did you do it? Well, 2 times 12 is 24. But remember, I also said in this course that numbers are meaningless without units, right? And so let's go ahead and look at 2 times 12 equals 24 and plug in some units. 2 feet times 12 inches equals 24 inches. Now, mathematically, does anybody see a problem with that? What is the difficulty?
The
Units. Right. We're looking at this saying, wait a minute, I've got it in the math we're going to be doing in here, both the coefficient at times, but the number math matters, but so does the unit math matter. So in this case, strictly speaking, if this is all I wrote down, 2 feet times 12 inches equals, well, 2 times 12 is 24, and feet times inches is feet inches, my units. My units are in feet times inches. Does anybody here understand what a foot inch is? Have you ever heard of such a thing? What's a derived unit? We come about it mathematically, a derived unit. But there is a way for us to come up with the correct answer. From feet times inches to equal, what do we want it to equal? Inches, right? How many inches? We can do that if we were to realize and use mathematically that 12 inches is equal to 1 foot. Okay? The 12 inches is equal to 1 foot. Now, yesterday I asked, if you have something and you divide it by itself, if you have a certain value and you divide it by the same value, what is the answer going to be? It's always going to be 1. Something divided by itself is always 1. So here conceptually what I'm saying is 12 inches and 1 foot are the same thing. Everybody agree with that? So if I have something divided by itself, the same volume, these are 2 different languages, let's say, but they say this, they mean the same thing. This is going to equal 1. But what it does numerically is translate from the language of feet into the language of inches. Because 2 times 12 is 24. Watch this. Feet times inches divided by feet. Divided by feet. Feet cancels feet, and I'm left with inches. 24 inches. So what you actually did was not just 2 times 12, but in your mind, hopefully what you did is 2 feet times 12 inches per foot equals 24 inches. See? The math is a little more complicated than you may have just thought, because we're always going to have to consider the units. Now, this unit conversion factor is what this is known as, a unit conversion factor. When I go from one language to another language, in the language of feet to the language of inches, I need something that's going to act as a translator. That's what this unit conversion factor does. And it starts with a statement of equality. A statement of equality, for example, in this case, I would have written down 1 foot equals 12 inches. That would be a known before I even get going. If I say we're going to do a problem that's going to be converting between feet and inches, you in your mind should say, well, I need something that relates feet to inches. I need something, a statement that's true that relates feet and inches. Oh, I know. 1 foot equals 12 inches. I know that's true. Well, guess what? If you have the unit you're starting with on one side and the unit you're ending with on the other side, you have your translator. You have your unit conversion factor right there. Because if I say this is A and this is B, and we know that A and B equal the same thing, if I say, well, then what is A divided by B? What does that equal to? 1. If they're equal, that's equal to 1. Well, what is B divided by A equal to? It's 1. So when I have a statement of equality like this, I can create my conversion factors. I can create where I want to go to. And here's how we work this out. Okay, I've given, my known is in feet. My unknown is my inches. So what I'm going to do is create a unit multiplier that puts what I desire to end in. I want to finish in inches, so inches goes on top. Let me use the same problem and erase it. Let me work through it again. Okay? Here's how I would set the problem up. And this is very basic, I understand, but trust me, it gets complicated later on, so we need to understand the principle, how to do it. And then later on, when you have these weird, funky units and big numbers, you're going to go, but wait a minute. I just need a statement of equality to create a unit multiplier, and we'll be fine. So we start with a statement of equality. 1 foot equals 12 inches. We have a question. 2 feet equals how many inches? I start by writing down what I've been given, my 2 feet. Now in the book, the practice they recommend that you do is to always put what you've been given over 1. Just create a fraction. 2 feet divided by 1. If I divide anything by 1, have I changed anything? No. 2 feet divided by 1 is still 2 feet. Then I create a unit multiplier. I go ahead and draw my divisor bar. I look at it and go, okay, I'm going from feet and I want to end in inches. I'm moving from the language of feet into the language of inches. I need a translator. All right. How do I do that? Well, I look over to what I want to end with, in this case inches, and I place that in the numerator. Then I look to what I started with, in this case feet, and I put that in the denominator. And then I look over to my statement of equality and say, do I have a relationship between inches and feet? Yes. How would I rewrite that with inches in the numerator and feet in the denominator? Well, that would be 12 inches is equal to 1 foot. So I bring that fraction, 12 over 1, 12 inches in 1 foot, and now I do the math. 2 times 12 is 24. 1 times 1 is 1. Feet in the numerator and feet in the denominator, since it's multiplication, they cancel each other, and I'm left with inches, which is what I was asked for. Okay? So 2 times 12 is 24. Anything over 1 is the same as itself, so in the answer I would very well probably just write 24. But my answer in inches is 2 feet equals 24 inches. And that's where on a test, even if we had a quiz right now, and I asked you, how many inches are in 2 feet? And you wrote down 24, it'd be right, but show me how you got there. And how did you get there? You created a unit multiplier that related inches to feet and converted them from feet to inches. So my given units, my given units. My desired units, my desired units. Do the math. Do the coefficient math part. Let's think about this maybe conceptually as let's say we lived in a society that was a barter society, okay? A barter society, and we bartered geometric shapes, okay? So rather than having bills with presidents' faces on it, we carried around squares and circles and triangles. So we had squares, circles, and triangles. And you're a currency exchanger. And you say, well, guess what? A square is equal to, give me a number between 1 and 10. 6? Okay, we'll go 6. So we'll say that 1 square is equal to 6 circles. And, Ray, you said 5, so 1 circle is equal to 5 triangles. Okay? And let's say that you go and you want to buy something, but you need to pay in triangles, and all you have are squares. Okay. So if I have 37 squares, how many triangles is that? If I've got 37 squares and I want to convert it into triangles, how many triangles do I have? Go ahead and start trying to work it out on your paper. Okay? Actually, let's make it easy first. Let's do a one-stepper. Let's just start with 1. Let's first just go to circles. How many circles do I have for 37 squares? And again, you might be able to do the math in your head, but please try to write it out as fractions using a unit multiplier. This whole process is known as the factor label method. That's what we're doing. So if you read, this is on page 10. Just give you maybe 15 or so seconds just to get ahead of me, just to see, so that you know if you're getting this or not. I have 37 squares and I want to convert that into circles. Well, I've been given 37 squares. And I need to have a unit conversion factor or a multiplier that's going to give me a certain number of circles. What are the units that I'm given? Squares. So I put squares in the denominator. And the units that I want to go to, circles, they go in the numerator. I look over here and I look for a statement of equality that relates circles and squares. 6 circles equals 1 square. Now I look at my units and I say, okay, in multiplication, squares cancel squares and I'm left with circles. Is that what I'm looking for? Yes. Now I know my setup is right. Okay? Check the units first. If I end with circles, okay, I'm pretty confident my setup is right. Now I do the actual coefficient math. 37 times 6. Let's see if that, look, 6 times 7 is, right? You said, what was it, Ray? 192? Okay, because I'm saying 6 times 7 is 42. It's got to end with a 2. 4, 6 times 3, 18. 19, 21, 22, right? Let's see. I'm sorry, do the math here. 37, 6, 2, 4, 18, 19, 21, 22.
Oh, okay. I did it wrong.
Okay.
Way wrong.
So we got 222 circles. 37 squares is equal to 22 circles, or 222 circles. And what we've just done is do the same thing we did before with 2 feet and 12 inches. It just wasn't obvious to you, right? It wasn't something you've done since kindergarten and could just figure out intuitively in your head. You actually had to sit down and do the math. Or look over there and say, okay, 6 to 1, 6 times 37 is 222. We can do the same thing in multiple steps, because if I asked you to give me what is this in triangles, well, you may have done it as, okay, let me convert it from squares to circles, and then let me do it again, 222 circles times, and again, we differentiate that between a 0 as 2,220. It's a very inconvenient unit, right? So it's 222 circles times something that's going to relate circles to triangles. Well, we got 5 to 1 triangles to circles, and that's going to give me my answer in triangles, which is what I'm looking for. Okay, good. Now it's 5 times 222. So 5 times 2 is 10, carry the 1, times 10 is 11, carry the 1 is 11. So 1,110 triangles is the same as 222 circles. Now this is a 2-step process. I went from squares to circles and circles to triangles. I could have done it all in one long unit by saying, okay, everybody just writing this down? Good to go? Okay, circle, cross that out. I could have just said 37 squares times something that's going to get me from squares to circles, and that's going to be 6 to 1. That's going to leave me with circles, but I'm not looking for circles, I'm looking for triangles. So I need something that's going to take me from circles to triangles, and circles to triangles is 5 to 1. Circles cancel circles, and now I'm left with units. Triangles, is that what I'm looking for? Yes. I'm confident my math is good. Now do the math. 37 times 6 times 5. This should give us the same answer, 1,110. Okay, but this is a 2-step conversion. I don't have anything that's going to take me straight from squares to triangles, so I have to go from squares to circles and then from circles to triangles. On the bottom of page 11, well, actually on the top of page 11, it lists out the steps in the factor label method. So the 5 steps we're going to do is right here. First, create a fraction out of the given. What they mean by that is, okay, I'm given 37 squares. Let me go ahead and make that 37 over 1. Why? Because we mentally like to keep, okay, multiply the numerators across, and then multiply the denominators across. And you hopefully remember that from algebra, right? We can just multiply across the top, put in the product, multiply across the bottom, put in the product, simplify the answer, and then move on. So create the fraction, what we're given over 1. Place the original measurement in the denominator, squares, we put squares down there. Second step, place the wanted unit in the numerator. In this case, our step wants us to convert the circles. Then place the numerical meanings from our statement of equality, 6 to 1, 5 to 1, whatever the case may be, and then do the math. Those are the 5 steps. So this will convert us from squares over to triangles, given those values right there. Any questions on at least the concept, the process? On that example 1.1 on the bottom of page 11, it's converting from 14,351 grams to kilograms. And we said yesterday the metric system is great and simple relative to, as compared to the English system, because the system is a base 10, which means we can just slide the decimal place around. However, we can also do this using the factor label method. In this case, 14,351 grams times something is going to equal a certain number of, we're trying to convert that into kilograms. Right? We have a certain number of grams, and they want us to convert that into a certain number of kilograms. Now this is the longer method to do this. But using the factor label method, what are going to be the units of my conversion factor right here? Somebody help me out. Well, let's look across. What do we start with? Grams. So grams has to be down here. And what do we want to end in? Kilograms. So kilograms has to be on the top. Do you know a relationship between grams and kilograms?
There's 1,000 grams.
Right. Right. 1,000 grams equals 1 kilogram. Remember yesterday we talked about the prefixes? Kilo means 1,000. So 1,000 grams equals 1 kilogram. That's a known. We always have that in our bag of tricks. Doesn't have to say it every time. We just know that. Okay. Well, I have a statement of equality that relates kilograms to grams, so I can use it to create the unit multiplier. What is the relationship? Well, 1 kilogram is the same as 1,000 grams. So I look at the units. Grams cancels grams. I'm left with kilograms, and that's what I'm looking for. So I'm pretty confident my setup is correct. So now I'll invest the time to go ahead and do the actual math of the coefficients. 14,351 divided by 1,000 is going to be 14.351. Because remember, when you're dividing by base tens, our shortcut is we're going to move the decimal place. In this case, since we're dividing by 1,000, we know we're going to move it 3 places because there are 3 zeros, right? So our shortcut says I'm going to move the decimal place 3 places. The question is, are you going to move it to the left or are you going to move it to the right? Well, here we're dividing, which means we're dividing by a large number, which means we're going to make our original number smaller. So when we divide by a large number to make our numerator smaller, we're moving the decimal place to the left. So we're going to be moving it to the left 3 places. The implied decimal is here, 1, 2, 3. And that's where the decimal is in the answer. So 14,000, think about it. How many thousands are in 14,351? 14 and a little extra, right? That's what this is showing me. I had 14 sets of 1,000, and then I had an additional 351 that not quite made it to the next 1,000 level. So 14,351 grams is equal to 14.351 kilograms. You could do that mentally by saying, okay, every kilogram is 1,000 grams. I've got 14.351 sets of 1,000. That's my answer. Or using the factor label method, write out this unit multiplier and come up with your answer by seeing that 14,000 divided by 1,000 is 14.351. In that vein, why don't you go ahead and start working on your own 1-1. Get a head start on me, and then I will join you in a moment. If you want to, yeah, Serena, if you want to just go ahead and get the problem from her. And 1-1, yeah. Yes, Ray.
What did you say? This?
Yes, on your own 1-1. Just go ahead and start working it. If you haven't done it already from your reading last night, then go ahead and start working it. And I'm not going to wait a long time. I just want you to start on it and get ahead of me, and then I'll join you in solving the problem. Use the factor label method, so write it out. Even if you can do it in your head, write it out. Because we're more concerned now that you understand the process than that you get the right answer. Both is great, but get the process right. And as I said before, if you're taking a test and you show me you've got the right process, that you can set it up, and yet you get the wrong answer, I'm going to assume it's because your finger hit the wrong button on the calculator or something like that. And I'm much more comfortable with that than here's the answer, it's either right or wrong, and I can't show you how I got it. Okay. Thanks. Yeah, just do the first one for now. We'll probably go through it, and then I'll have you do probably the third one. third or second, not sure yet. So I would set the first problem up by start by writing down what I've been given, right? The problem says a student measures the mass of a bag of sand to be 9.321 grams. Is it 9 point or 9,000? 9,000. Even with these no line bifocals, that looks like a period to me. Okay, so it's 9,321 grams. Because if it was 9.321 grams and we put it in kilograms, it would be a very small number, right? Trust me, we're going to get much smaller numbers than that. Much, much, much smaller numbers than that. Like to the negative 20 thirds and things like that. So, but let's start with to the 0. Because anything to the 0 is 1, right? So what we're talking about now is times 10 to the zeros. All right. 9,321 grams. The question says, what is the bag's mass in kilograms? So I know I've got something that's going to need to be converted to end in another something that's going to be in kilograms. That's just from the word problem. And some of you that may have struggled with word problems in math, the hardest part right now is going to be get the setup. And as you go through the modules, it's going to be get the setup. How to read the problem and set it up as a math problem so I can actually attack it and solve it. In this case, 9,000, hopefully if you look at this, you could kind of write the question. If you hadn't heard the question, but you saw this on the board, you should say, okay, I'm trying to convert 9,321 grams into kilograms. Because this is a standard setup to do that. I'm given grams, and so in my conversion, where do grams go? Where's the unit of grams go? The denominator, in the bottom, correct. I'm looking for kilograms, and so the unit in the numerator is kilograms. I need something that relates kilograms to grams. We've just talked about that. 1,000 grams is 1 kilogram. Looking at the units, grams cancels grams, leaves me with kilograms, and that's what I'm looking for. Confident my setup is correct. Do the math. 9,321 divided by 1,000 is 9.321 kilograms. That's on your own, number 1. On your own, number 3. A professional basketball court, or on a professional basketball court, the distance from the three-point line to the basket is 724.0 centimeters. What is the distance in meters? So I'm going to take what I've been given, convert it some way to end with a measurement that's in meters. I need something that's going to relate what to what? Centimeters and meters. I need to relate those two things. I need a statement of equality, okay? Or some kind of relationship between those two, preferably a statement of equality. So something that relates centimeters to meters. Does anybody know what that relationship is? Remember what the centa means?
100 centimeters a meter.
Okay. So 1 meter equals 100 centimeters. How do I know that? Because centa means 1/100th. Because I would then be able to say that 1 centimeter equals 1/100th of a meter. That's technically 1 centimeter is 1/100th of a meter. Another way to write that is if I multiply both of those by, by 1,000, I end up with 1 meter is 100 centimeters. Okay? So that's my statement of equality. 1 meter is equal to 100 centimeters. So I look at my problem, the word problem I've written out now as a formula form. I need to have centimeters in the denominator. I need to have meters in the numerator because I'm leaving this and going to this. So I'm confident my setup is going to be right. Now how do I relate meters to centimeters? It's right over there, 100 centimeters is equal to 1 meter. And so my answer is 724.0 times 1, which is going to be 724.0, divided by 100. Dividing by 100, I'm going to move the decimal place 2 places to the left. Boom, boom, it's 7.240 meters. And hopefully that makes sense when you say, well, each meter is 100 centimeters, this would be 724. Just do the math. Multiply by 100 over 2. Yes, that's right. Now, this isn't part of this unit, but it is something I want to discuss here, is what is the difference between 724 centimeters and 724.0 centimeters? Is there any difference? If I said, measure out a piece of string that's 724 centimeters long, and then I said, measure out a piece of string that's 724.0 centimeters long, would the two be different lengths, or would they be the same length? The same length. However, those two pieces of information, the difference between 724 and 724.0 centimeters, communicates something to me as a scientist that's significant. Okay? We're going to find out later that what we're talking about here is an issue of precision. Remember when I was taking the mass of the balloon on the triple beam balance, and I went over and said, this balloon has a mass of 2.54 grams. Well, over there on the triple beam balance, there is a mark on there that represents 2 grams. And there was a mark on there that represented 2.4 grams. But there wasn't a mark on there that represented, I think it was 2.45 or something like that. That next place wasn't on there. I had to estimate that place. I had to look and say, okay, here's a mark for one, here's a mark for another. It's actually right in between the two. It looks about, and I did an approximation. See? So whatever my instrument is, I could take it out as far as it would read, and then I could estimate the next level. But I can't go any farther than that. I wouldn't say it's 2.5473 grams, because I'm guessing then 2 places beyond what my instrument read. For right now, all I want you to get is, yeah, I understand in the math, or in the concept of give me 724 apples or give me 724.0 apples, there's not going to be any partial apples there. But because there's a 0 on here, it's significant because it tells me that the instrument that I had to measure this with was much more precise than the measurement that I had for this right here. Let's say for this one I ended up measuring this with a ruler, but in this one I ended up measuring it with a buy from Home Depot laser distance finder. Okay? It could be a little more accurate than the other one. It's not that it's a different distance, but it does tell me that the instrument I use to measure it is much more precise. And we will get to measurements where these are carried out to the thousandths or 10,000ths or 100,000ths place. And that's communicating to me is that I can be confident in that measurement out to that point, but not beyond it. I can't just extrapolate out and add trailing zeros just because I arbitrarily want to. I've got to have a scientific, which becomes a mathematical reason for doing that. On the bottom of page 12, and I know this is just a little bit beyond our reading for today, but basically when we're converting between unit systems, and this is going, as they show you on here, like for distance, going from inches to centimeters, mass going from slugs to kilograms, and volume going from gallons to liters. As we're translating between the metric system and the English system, the setup is going to be exactly the same thing. On the chart, it gives you some statements of equality. 1 inch is equal to 2.54 centimeters. Okay. Well, if I know that 1 inch is 2.54 centimeters, I've got inches that's in my English system, and I've got centimeters, which is in my metric system. Guess what? I now can convert anything that I can get into inches into centimeters. So if I know that something's in yards, well, I can divide that by 3 to get it in feet, and then divide that by 12 to get it in inches. And then I can convert it to centimeters, and then I can convert it to meters, kilometers. I can convert it to anything. But this right here is kind of like the Rosetta Stone of the math problem. You guys know what the Rosetta Stone is? I mean, it's more than just the program that you sat in front of, to take Spanish 1 and 2. Rosetta Stone is significant in that it was actually a stone. And again, you said you're familiar with it, but are you truly familiar with what the Rosetta Stone is? Okay. So, I mean, it's a key piece. If we had not found the Rosetta Stone, we'd have difficulty in translating between Greek and Egyptian and all these languages, because the Rosetta Stone had the same text written in multiple languages. And you can say, hey, these symbols in this language mean the same thing as these symbols in this language, which I don't speak this language, but I can go from my language to this language. And now, because of the Rosetta Stone, I can go from this language to this language. Hey, guess what? I picked up a whole language because I have a way to relate them. These are ways to relate them. So I can go from English to metric distance-wise because I know inches to centimeters. And that's what you're doing here. If you look at example 1, 2 at the bottom, they're converting from inches to centimeters. 37.8 inches going to centimeters is going to be the same thing. Inches, centimeters, 2.54 to 1. Do the math. Same concept, just you're working between metric system and the English system. And then just kind of to encourage you, if you flip over to page 14, and I know you're not there yet if you're on track for the reading, but on example 1.3 on page 14, it is a two-step conversion. It's just like I showed you on the example going from squares to circles to triangles, okay? This is a two-step conversion. So example 1.3 walks you through going from kilograms to milligrams. How do you do that? Well, they're going to take you from kilograms to grams and then from grams to milligrams. A two-step process rather than a one-step process. And so it's real important for you to practice the setups, practice writing these out. Even if you look at them and you think you know the answer in your head, even if you put down a number and you look in the back and say, hey, I got the right number, write it out. Write out the conversion factors. Make sure you understand the process, because once we get into applying this, you'll be amazed at the kind of funky units we start getting. And you really can't, at that point, stop and try to figure out, do I divide by 1,000 or do I multiply by 1,000? Just write it out. I mean, nobody's going to take credit off because you had to write down a factor label method of how to convert from meters to kilometers. Better to do that, because in about 3 or 4 weeks, this is going to be like baby steps, right? You're going to go, man, I don't want to write that down. Write it down and get it right. I'm not going to criticize you for writing it down. Unless, of course, you write it down and it's all funky and wrong and stuff like that. And then we need to talk about, do you really understand how to set these things up?